Okay, well, it's great to be able to talk to you from the UK. I happen to be here. I just arrived. I was in Rome on Tuesday and back in the UK, and tomorrow in Abu Dhabi. So it's good to be able to speak to you from my home in England. I think it's interesting to think that that the science people think that you should, when you do research, that you should do very important things, and I don't do that. I just do things that interest me personally. I don't worry about what is important to other people. I think it's important that you personally are, if you're doing science and doing research, curious about some things that you see, some work that you know about, some technology that interests you. And when you start to get puzzled, you look into it in a bit more detail. And sometimes that's the way to discover something that people haven't discovered previously. So when one thinks about this, it turns out that the most unusual discoveries and the most important discoveries are those which were not known beforehand, and where it was impossible to predict beforehand that they were going to be important. And in the case of our discovery of the buckyball, it was a very simple little experiment which was puzzling. It didn't look very important. It looked like a very straightforward experiment. In some ways, it was a straightforward experiment. By accident, really, went into a laboratory of Rick Smalley at Rice University, who had built a very impressive system with a laser which vaporized metals. And I thought, well, if you can vaporize metals, you can vaporize carbon. And if you vaporize carbon, you can produce the atmosphere in a carbon star, a cool red giant carbon star. And I thought this was interesting because sometime earlier we had discovered that carbon molecules were in space, and that some of these molecules seemed to be coming out of the carbon star, and I wanted to simulate the atmosphere in a carbon star just to check on my thoughts. They weren't important thoughts, they were just thoughts at the back of my mind. And when we did that, we found that it was exactly as expected, plus a surprise that there was something totally unknown and unexpected turned up in our experiment. It was a molecule with 60 carbon atoms, and we decided that maybe this molecule was arranged in the shape of a soccer ball. And we discovered that that's actually what it was. It was a molecule in the shape of a soccer ball. And I had earlier been fascinated by Buckminster Fuller, who had designed the geodesic domes. And this was a clue to deciding what the structure is. In fact, a soccer ball with 12 pentagons and 20 hexagons is a geodesic dome structure. I didn't realize that until after the event. Anyway, my colleague, Professor Smalley, Rick Smalley, had developed this apparatus, and it was my friend Bob Curl who had said I should go and visit him to see this fascinating new apparatus. And so we, as I say, we got together to do this experiment, and out of this came this total surprise that there was a third form of carbon. Carbon has several structures, but only at the time two were well defined. One was diamond, which have in diamond rings, and the other one is graphite, which you have in pencil leads. And we discovered a third well-defined form, which was a molecule, the buckyball, with 60 carbon atoms. And that was so exciting at the time, and it excited other people because it's so beautiful and symmetric, that it became a sort of icon for nanotechnology. And from then onwards, whenever people talk about nanotechnology, they show a picture of this soccer ball shaped structure. Now there may be 1,000 research papers every year on this. And then when people look very carefully at it and were able to make it, they found in the same system there were nanotubes. These are tubes of carbon, which are very exciting because they theoretically can make the most strongest material we could ever make. They'll probably make aeroplanes so strong that when an engine fails, they would just glide. So strong and light, maybe 50 times stronger than steel, effectively, and 1/6 the weight of aluminium. So I think it sounds very exciting for the future. And now there's yet another form called graphene. These are flat sheets. They're all related. Our buckyball is a sheet which is rolled up into a ball. The nanotubes are sheets which are rolled up into tubes. And graphene is the sheet, flat sheet by itself. And all these carbon systems are now being studied very carefully because they promise to be paradigm-shifting elements in the development of nanotechnology devices in the 21st century. So it's a very exciting time. However, the first thing I would say is that when people think of the Nobel Prize, they think you have to be very, very clever. That's not the case. I'm not any cleverer than any of you. Also, you think, oh, you've got to do an important experiment. Well, it didn't look important at all at the start. It was only after the experiment that we discovered that it was important. And I didn't aim to win any prizes. I was just interested in the results of the experiment. So an important lesson is don't do science to win prizes. You do science because it interests you. It's something you're probably good at. And it's a way of earning a living. It's a good job. And that's what it was to me. And the fact that this very simple, rather in some ways unimportant experiment led to something that led to the Nobel Prize is really an interesting lesson. And probably the other thing is that I think you should think that when you're doing something, never do something second rate. You should always do something to the best of your personal abilities. And if you do that every time, you'll find that you'll do things better than other people, and you may well be very satisfied with your results. Okay. Hello, Filippo. Hello, can you hear me? Okay, I now am waiting for some questions. Okay, any questions coming in? 45 years old. It's in 1985 when we discovered the fullerenes. So usually you find that mathematicians are younger than, and physicists are younger than chemists. Okay, there are many ways that nanotechnology will be applied in the future, but I think the first thing to really recognize is that it's not new. There are several definitions of nanotechnology, and the first one, and the best one as far as I'm concerned, is atom by atom, molecule by molecule, assembly of a complex and or functional system. Okay? Now, in modern technology, in computer technology, that is top down, where you take a piece of silicon and you carve the elements of a chip onto the chip. Now, the question is, a computer is not a nanotechnology device, it's top down. The question one might ask is, could you create a computer by bottom-up technology? Can you do it by chemistry? Can you pour things together so that atom by atom, molecule by molecule, you can create a computer? Well, if that's the definition, it's already been done, because your brain is a computing device, and that has been created atom by atom, molecule by molecule, protein by protein into your brain on the basis of a DNA blueprint. So that tells you that anything's possible. The role of creativity, basically, creativity is everything. When one is a child, you're creating things, but many of those things have already been created before when you're small, because you learn. You see how things are made. But then in science and also in life, probably the most important aspect is to create something that is personal, something that only you could have done. And basically it makes life worthwhile. What would I study nowadays? I still would study science, but also art and graphics. As far as I'm concerned, I like science and I like art and graphics, and in fact, I do still do some graphic design in my spare time. So I like, and also other things like not study but music, and I like music as most people do. And I played tennis as well. So these were things I did when I was a student and later on. What do I study nowadays? Well, I still I collect a lot of books on art and graphics and design. On the science side, I'm still trying to understand how the buckyball forms and doing some nanotechnology. But still it's very similar to what I was doing before. I think it doesn't matter what you get involved in, as long as it's something that you are prepared to do to the best of your ability. I don't think it matters whether you actually enjoy something. Enjoyment is a very strange word. I mean, I enjoy not doing work. I mean, I enjoy having a meal. I think what one should do is do something that you get so involved in that time doesn't matter, where you are prepared to spend from the moment you'll wake up till the moment you go to sleep, making sure that whatever it is you do is the best you could possibly do. I'm not an expert on the future of energy. It's not really my sort of area. But it seems to me that there are important advances. and that is we need to work out how to split water into hydrogen and oxygen. If we can, it requires 2 photons to break the oxygen-hydrogen bond. So we have to have a catalyst that can actually take the energy of 2 photons and focus it into splitting the oxygen-hydrogen bond. If we can do that, then I think we'll have unlimited sources of energy, because we'll take photons from the sun to break the water into hydrogen and oxygen, and then store these, and when we need the hydrogen and oxygen, bring them together and burn them back into water and use the energy as we need it. Well, I think so. I think it's a long way to go, because we still don't have very good control over making nanotubes. But theoretically, you can probably make almost anything out of nanotubes. I think but we still have to have a major advance in chemistry, in our synthetic chemical ability. At this moment, it's very, very difficult to make nanotubes which have the right sort of shape and structure. You can make them, but they come in all shapes and sizes. And as you well know, if you're going to make a machine, you have to have absolute control of structure, and we don't have that at the moment. Well, first of all, it's not a superconductor. It's actually a ballistic conductor. That means that the electricity that goes in one end, all of it comes out at the other end. It doesn't actually generate a current by itself. You have to put the current in. But that means that it will be very good for the transport of electricity, because there should be no losses at all. But we still have to solve the problem of making nanotubes that are long enough, and this is still a major problem in synthetic technology. Well, I don't know. I mean, I lived for 37 years in the UK, and I was very happy there, and I was able to do research that I wanted to do. So that was good. But I think it's also very good in the USA and France and European countries, probably Australia and Japan, maybe now China. The problem is that there's a lot of pressure now, economic pressure, on research workers to do research that appears to be important before you do the science. And that's not very good, because as I pointed out in our discovery, it wasn't obviously important to do this experiment. We realized that only after we'd done it and we found this amazing serendipitous discovery that we found that it was important. And I think that is one of the lessons we have to learn, or that should be learned, but it's not learned very well. So I think the main thing is to find a way of doing the things that interest you personally. And I was able to do that in the UK and presently in the USA. And I'm sure if I were in Germany or many of the Western countries, we could have done the work we did. Maybe things are a bit more difficult now because of the economic situation. There is a possibility of fullerenes being used in pharmaceutical applications. One of them that we're looking at is that you can put a radioactive element on the inside of a buckyball, and now that atom is trapped in there, not chemically but physically, and it can't get out. And so if that radioactive element happens to be a toxic one, and most of the radioactive elements that are toxic that are radioactive are toxic, then you can get around the problem of things like sort of byproducts of the chemical toxicity by putting the atom inside a buckyball. So that's one thing that people are looking at. No, the answer we didn't, but we did know it was important because when we started to get strong signals on a Monday. The experiment started on a Monday, and by Wednesday we found out there was one particular cluster, because we could see clusters of carbon atoms with anything from 3, 4, or 5 atoms to 100. And in certain experiments, the set of carbon clusters with up to 30 atoms were strong, but then under different conditions, the set that were higher than 30 carbon atoms were strong. But whenever the set that were up in the high range, there was always C60, the one with 60 carbon atoms, which was much stronger than everything else. And by playing around with the experimental conditions, these were carried out with the students, Jim Heath, Shoma O'Brien, and Yuan Liu. We found that the 60 carbon atom species could sometimes be made 30 to 40 times larger than any of the others. And I think Sean was the first person to get it 30 times bigger than anything else. So that it was clearly, when that was the case, it was clear that this was very important. But we didn't know the grandeur of it until a few days later, maybe 6 or 7 days later, because the buckyball was born on I think the 4th of September, 1985. That's when we recognized that it was significant, and we asked questions as to what it was. And on the Tuesday, a week later, we decided that it was the shape of a soccer ball. And at that point, we realized that this is really quite exciting and fascinating, and we were rather pleased with that particular highly symmetric structure. It was very exciting at the time. Well, I'm not an expert in medicine, but it's quite clear that nanotechnology has many different sort of aspects, and one certainly is in tiny machines, tiny devices that are much smaller than the devices we have on Earth. I mean, for instance, we have made a little spring, a spring like a concertina, which can just do this, and that is probably 1,000,000 times smaller than a standard spring. So we can make little devices, and if we get better and better at it, we should be able to make little machines which probably can go inside the body and analyze parts of the body for, say, cancer and things like that. And there's no doubt we should be able to make probes that are so fine you will not even notice them. That seems to be a possibility. And certainly the nanotubes should be so strong and thin that you can just stick them through the skin into different parts of the body without damaging anything, because they will pass through the micelle layers. So it's a very exciting time. I don't know the answer to this biocompatibility. I think it's not soluble, first of all, so it's not really poisonous because it's a solid, and you can't drink it, and it won't go through the skin. I think it's too big for that, but I don't know about that. But at this stage, I don't know about biocompatibility. It's not something I've looked into, and but there's no doubt that you don't want to. I don't think you want to drink it particularly. Well, it was very exciting when we realized that this molecule had the shape of a soccer ball because we'd never heard of it. I mean, it had been conjectured. There was a Japanese scientist, Eiji Osawa, who had actually thought of it in 1970. And I think that was a brilliant sort of piece of imagination. But we actually discovered how to make it, and that we actually proved that it actually existed. So we actually discovered it. And once I remember thinking that as I was flying on the plane back to England, because I discovered it during a visit to Rice University in Texas, and I thought that it really, I felt the plane could probably fly without the engines. I was on such a high. Probably not. I mean, you could put a nitrogen atom. You can replace one carbon atom by nitrogen, and that was done early on. And we, in the last year, have replaced one of the carbon atoms by boron. But you won't be able to make a structure quite like C60 out of other elements. So I don't think so. So I think it's definitely a one-off structure. Well, I mean, a lot of questions so far. And they've been very interesting to answer them. But if you have any more, I'm happy to answer plenty more. Well, I, to some extent, already covered this. By far, the most important thing is to be curious and be interested in how things work, but to have determination to solve the problem and not give up. I mean, I think you should, as I said before, you shouldn't do anything unless a first-rate effort will satisfy you. Second-rate efforts will satisfy you. Should do something else because, by and large, you just discover nothing if you have a second-rate attitude to what you're doing. And because, you know, a lot of research has been done, and so it's really quite hard to do something that's new. But I think there are lots of problems that are lying around and lots of puzzles, and I've always been able to find lots of puzzles and try and sort of follow them through. So I try to find out how things are working. So for a good researcher, it is to have curiosity, always in a first-rate effort, but also you must be questioning and look at evidence. It's very easy to be fooled, and the easiest person to fool is yourself. I usually say that if you have an observation and you have a hypothesis, you should follow my 4 out of 5 rule, which is think of about 5 different experiments to test whether your hypothesis is correct. If 4 out of 5 fit, then your hypothesis is almost certainly right, with the accent on almost. And if only 1 out of 5 fits, your experiment or your hypothesis is almost certainly, again, with the accent on almost certainly wrong. And let me give you an example. One say, well, do we have climate change? Or, and this is a very contentious area at the present time. Ask yourself, do you believe that there is climate change? Well, think about 4, 5, 6, 7, 8, 10 different observations you might make to check on this. So the first one would be, what about the average sea level? Well, the average sea level has risen over the last year by about 1 centimetre to 1 inch. What about the average temperatures? The average temperatures have risen over the last century by about 1 degree. And in fact, the rate of increase is higher in temperature than it's ever been before. Is there carbon dioxide in the atmosphere? Yes. Is it going up? Yes. The Hawaiian experiments indicate that that's true. Are there more hurricanes? Are animals moving from their natural habitats? All these things you have to look at, and then don't accept other people's word for it. Just look at the evidence yourself and say, yeah, 4 out of 5 seem to indicate that we've got a global warming on our hands. And I now follow this. I don't tell people I believe that there's global warming. I say, look at the evidence from, as I say, sea level rise, glaciers receding, 9 out of 10 are. Then some are miles back from where they used to be. And just say, well, this is the evidence that indicates to me, as a sort of fairly average, not just a scientist, that we've got a problem. So those are the aspects that make a scientist. And there's one other thing that's very important about science that's not understood. The first thing is that science has various aspects, and one of them is that science is a store of knowledge of how the universe and the natural world works. And that we've discovered that. Human beings have discovered that, and they've written that all in books, and it's on Wikipedia. The second is the technology, and we apply our knowledge for technology, hopefully for the benefit of the human race. So that's applications. And then there's obviously the scientific method, the way that we discover new knowledge. Do we make breakthroughs? How do we discover something new, like the buckyball? That's a scientific method. So those are 3 important aspects. But there's something important than that. And that before science became so useful and valuable, from things like penicillin, food, to name it, mobile phones, long before that, had another name. And that another name was called natural philosophy. It was a philosophy. It was a cultural, intellectual exercise. And this is what it is. Natural philosophy is the only philosophical construct we have devised to determine truth with any degree of reliability. I'll say it again. Natural philosophy is the only philosophical construct we have devised to determine what is true with any degree of reliability. All other constructs, political ones, economic ones, religious ones, they're all man-made. They've all been evolved in time, but there's no evidence to confirm any of these. Nothing that would satisfy me. For instance, when I come in at the airport in the USA, they don't just take my word for my name. They want to see my passport. When I get gas out of the pump, they want some evidence of who I am. They ask me for my zip code. And now they're checking on the name. So these are very interesting aspects. So basically, more important than anything else for science is not to accept anything, absolutely nothing, without evidence. Because once you start to accept things for which there is no evidence, um, the world becomes a worse place. For instance, you can get awards and things of this nature, but you have to be honest about what you're doing. So, effectively, I think you think about that. Don't know the answer to which are the most important reactions. I mean, I think in the future, putting hydroxyl groups on the outside to make soluble will be very important in pharmaceutical applications. Obviously, halogenation to allows you to produce new synthons, but at this stage, I would say the reaction to put hydroxyl groups on the outside to make it hydrophilic rather than hydrophobic, that would be a very important one, particularly in the pharmaceutical area. Yes, I can. Uh, I don't have any more questions. The last one was the organic one. Yeah, 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 no problem. No problem. Yeah, I hope the next somewhere. I hope You too. It's great to work with you. One more question, or is that it? Okay, see you. Bye. Okay, okay, ciao.